Hello Year 10s, today we're going to look at linear optimization, otherwise known as linear programming. Now this is an amazing use of linear inequalities, and while I'm not going to insult you and say these are real life examples, our first one involves a super duper boot company for example, this skill in mathematics is used in real life to determine optimal outcomes. And the example I'll run through today will take a little while, and so will the assignment you do on this subject, on this topic. But I'm hoping it will give you some skills that you can then use later on. And it's not strictly within the Year 10 maths, but it's a very interesting region of maths, and that's why I'd like to explore it further. So, our example today involves the super duper boot company, which makes only two styles of boot. The super boot and the duper boot. Already you're excited. Now, there are only 20 pairs of boots that can be made each week. The super style takes 4 hours to construct, the duper style takes 2 hours. There are 60 hours of time available in the construction department. Super style takes 4 hours to polish, test, package, while duper style takes 6 hours to polish, test, package. There are 108 hours available for these tasks. Super style retails for $45 each, the duper style retails for $60 each. What is the optimal combination of boots to be produced to maximize profit? Each of these questions has something in common. Each will have products or a list of things to be built out of ingredients, or ingredients being either people's time or literally ingredients of what you can put in. And essentially, you can build stuff, and then as you build things, construct, manufacture, etc., there'll be an objective function. Typically, the objective function is given to you something like this. You're going to make money somehow, how do you maximize it? Or how do you minimize losing money? And what we're going to do is set up a series of constraints, or a series of things we must satisfy that will give us a list of feasible solutions. So one possible solution might be we could make two super boots and two duper boots. Really wish I hadn't chose this example now. That's going to get me throughout this entire explanation. So we could just produce 4 boots a week. 2 super, 2 duper. And that's a feasible solution here, but it might not be the optimal one. Similarly, we might be able to produce, well, one of you's probably thought by now, why don't you just produce 20, because you're allowed to make 20 boots, 20 duper boots. And the reason you can't make 20 duper boots is probably along the lines of each duper boot takes 6 hours to polish, 26 is 120, you don't have 120 hours in a week available, you only have 108. Alright, so the obvious answer of 20 the most expensive or 20 the most profitable would be the obvious answer, but you can't do it because of the constraints. So we're going to set up constraint equations, feasible region, shade it in, and then look at how we can find the optimal combination of super boots and duper boots. So, typical way to start these is draw up a table showing the information. I'm going to let the number of super boots be X and the duper boots be Y. Now, the construction hours, if super style takes 4 hours to construct, then it'll be 4X construction hours, and duper takes 2Y construction. The polish test package, again, is 4X for super and 6Y. Okay, now, each one of these pairs will give us a constraint. And those constraints, or linear inequalities, look like this. X plus Y is less than or equal to 20. That means the sum of boots produced is less than or equal to 20. 4X, apologies, 4X plus 2Y is less than or equal to 60. That's the construction department taken care of. 4X plus 6Y is less than or equal to 108. Now, they are inequality constraints, and I'll just give you 2 more. Firstly, the number of super boots must be greater than 0, and the number of duper boots must be greater than 0. The reason we include them is to eliminate negative answers. It would be possible to have negative answers which would represent the shoes the company buying a type of shoe instead of making it and therefore somehow recouping the hours. It doesn't make sense to make negative boots, which is why we've included those last two. Alright, remainder of the example, we're going to graph those. I'm going to pause it, type them out, and then it makes graphing them quite quick and easy for me. Cheers. Alright, so type them up. Many of you will notice the error I made before. That is clearly y is meant to be greater than or equal to 0. Alright, type them up. Now we want to show these on a graph. Last video I showed you how to do it by hand, and in the assignment you will be expected to do it by hand. You can graph each of these quite comfortably, I'd hope. One way to do it would be to find the x and y intercepts and draw a line going between them. Alright, so if I put them into GeoGebra, this is the first inequality. X plus y is less than or equal to 20. And you can you can see they've shaded the region they require. Less than or equal to 20. 4x plus 2y is less than or equal to 60. Looks like that line there. And the other one. And now greater than or equal to 0. Greater than or equal to 0. And this is a little ugly, and it's ugly because they've shaded the region required. I can't make GeoGebra do it the way we do it by hand and shade the region not required. However, the region of feasible possible solutions goes from here to there, to there, to there, to there. Everything in this space is a possible solution. Alright? Alright, so I've cut this GeoGebra graph into OneNote, and here we're looking at the shaded region, at a feasible region. Recall that anything in here is feasible. Now, really, it's not an infinite set of solutions, because if it was an infinite set, that would imply that one possible solution would be 3.5, 3.5. And while you can make 3.5 boots, really it doesn't make a lot of sense to. So our feasible solutions are really these points here. We could make no, none, one of each, etc. They are distinct dots. These dots are coming out larger than I expected. All of those are possible solutions. And just remembering here that the x-axis is the number of super boots and the y-axis is the number of duper boots. X, super, y, duper. So one possible solution, for example, would be to produce 6 super boots and 6 duper boots. We could do that. Now there are lots and lots of points inside here, and the question is, how do we know what the optimal one is? Well, there are two things we use to find that. Firstly is what we call our objective function, which is, in our case, cache. And the objective function looks like 45x plus 60y equals, say, profit. And we want to make that p number as big as possible. So what values for x and y do we sub in order to make it as big as possible? The second thing we know, or I'm about to tell you rather, is that the optimal solution is always a vertex of the feasible region. So, for example, 6, 6 will not be one of the optimal solutions, or will not be the optimal solution because it's not a vertex. We can do better than somewhere in the middle. All we have to do here is find where the vertexes are, and they are possible optimal solutions. One of them will be better than the others. So the numbers I've written on there are the vertices of our feasible region, or the corners of our feasible region. One here at 0,18, one here at 6,14, 10, 10, 15, 0, and 0, 0. Alright? Those are the only solutions we're going to consider and sub into the objective function. All others are not worth considering. For example, this one out here isn't worth considering because it's not within the feasible region. These ones within the feasible region are not worth considering because they're not going to be an optimal solution. It'll be one of those 5 corner points that is optimal. And I realize I haven't provided a very convincing argument for why the corner points are optimal. For now, take it on faith. Apologies, I know that's a terrible answer. Alright, so what you do here is list vertices and then profit here. Profit for each vertice. So our first vertice is 0, 0. And if we sub 0, 0 into that equation above, we get 0. What about 0, 18? Well, if we sub 0, 18 above, we would get 45 lots of 0 plus 60 lots of 18. Let's have a shot. Yeah, I can't do 60 18s in my head. But that would get us $1,080. And that was one of our possible solutions we flagged at the start, that all we could do is produce duper boots, and maybe that would be our best. Alright, but let's look at the others. 6, 14. That would mean 45 times 6 plus 60 times 14 is 1,110. It's interesting. Let's try 10, 10. 10, 10 is 450 plus 600 is 1,050. Now let's try 15, 0 is 45 times 15, which is 675. Our optimal solution then is the point 614. If we produce 6 super boots and 14 duper boots, we can do that within our resources, and that is the optimal solution. Essentially, the reason why we don't consider points, or one of the reasons why we don't consider points within this region here, because that would represent wasted resources. Say, take this blue line here. That blue line represents the total number of boots adding up to 20. It doesn't make a lot of sense to produce a number of boots less than 20. Hence why we aren't considering points down here. Similarly, it doesn't make a lot of sense to not use all the construction hours or the production hours. So we'd really want to find somewhere that is on the vertex, as in pushing all those constraints as far as we can to maximize the use of our resources in order to maximize our profit. Alright, I apologize that's gone for a long time, but let me just run through these because these are big questions. You'll set up constraints from the equation, graph those constraints, and find where they meet. Remembering to actually gain these points, yes, you can do it in your calculator, but similarly you can do it algebraically if you want to find the meeting point of those two lines. Solve that one and that one using elimination. Once you've got those points, list down the possible vertices, look at your objective function, and sub them into the objective function one by one until you show the optimal outcome answer in a sentence. Yep, they are large problems, and they take a lot of work, but they're very interesting in terms of finding solutions you wouldn't have necessarily thought of. Because remember, our initial reaction to this problem was, well, let's produce all of the most profitable boots and none of these ones. Whereas really, we can do slightly better than that. That would be this solution. Our yellow highlighted one is even better. Alright. Thank you for watching this for so long. Good luck in your assignment. Follow the similar steps, and remember, in the assignment, your explanations are as important as your answer. Thank you very much.